Unit 2 is pretty extensive, although it's focused on solving all kinds of one-variable equations. We first began solving linear equations in one variable. We then progressed to solving quadratic equations using 4 different methods. We then learned higher degree polynomial equations by factoring or by using the rational zeros theorem. In this video, we'll learn how to solve radical equations and rational exponent equations. While now we're going to focus on equations containing a single radical. To solve an equation that contains a single radical, do the following. Number 1, isolate the radical. Then raise both sides of the equation to an appropriate power to eliminate the radical. For a square root, square both sides. For a cube root, cube both sides, etc. And then solve the resulting equation. That resulting equation may be linear, it may be quadratic, it may be polynomial. You'll have to understand which category it belongs to in order to apply an appropriate process to solve it from there. And then finally, check the solution in the original equation. Now, sometimes when you solve a radical equation, even though you do all the algebra right, you end up with extra solutions that don't balance the original equation. We call these extraneous solutions or extraneous roots. We will not include these in our solution set, so be sure to disregard extraneous roots. Let's begin with example 1. Solve the following radical equations and be sure to disregard extraneous roots. So we have the equation containing a single radical, square root of 2x minus 1 equals 3. Notice the radical expression is isolated by itself on the left side. So our first step is to eliminate this radical. And we're going to do that by squaring both sides. So I'm going to square the left side and square the right side. Now, the square root and the exponent 2 are inverse operations, so essentially they cancel and leave behind the radicand 2x minus 1. And over there on the right side, we have 3 squared, which is equal to 9. We can add 1 to both sides of the equation to get 2x equals 10, and divide both sides of our equation by 2 to get our apparent solution, x equals 5. Now, before we make our conclusion, we want to make sure that this balances the original equation. So I'm going to go all the way back to the original equation and replace our variable x with the value of 5 and test to make sure we have a balanced equation. So under the radical, we have 2 times 5, which is 10, and 10 minus 1 is 9. So we have the square root of 9 equal to 3. And we know the square root of 9 is 3, so we certainly have a balanced equation. So our solution, x equals 5, is correct. Okay, that wasn't so bad. Let's try another one. Again, our radical is already isolated on example B, so our first step will be to square both sides. We just have to be a little bit careful with that right side. So I'm going to square the left side and square the right side. When we square a square root, it cancels out, and we end up with the radicand 2x plus 1. Now again, be very careful over here on the right side. It can be tempting to want to distribute that exponent, but remember, you can only distribute an exponent across a product or a quotient, but not a sum or a difference. So in the case that we square a binomial, I encourage you to write that binomial twice so you'll remember to FOIL it out. That way you won't be missing your middle term. So when we FOIL, we end up with x squared. Outside and inside terms are both minus 1x, and those combine to give us a net middle term of negative 2x. And last, we have plus 1. Now over here on our previous example, when we eliminated the radical, we ended up with a linear equation, and we isolated x to solve the equation. Here, when we eliminated the radical, notice we have a quadratic equation. Because the category is different, I'm going to apply a different process to solve it. Now, generally, I'm either going to try to factor it, or to do the quadratic formula, or perhaps the square root method. But if I think about factoring or the quadratic formula, they both require us to have our equation equal to 0. So I'm going to work on moving all of my terms over here to the right side. The reason I'm going to the right side is because my highest powered term is over here, and it has a positive leading coefficient. I find it easier to factor with a positive leading coefficient, So I'm moving all the terms over to join that trinomial. So I've got the 0 I need over here on the left. Combining like terms on the right, we have x squared minus 4x, and it looks like our 1's cancel. Okay, it's quadratic, but we should be able to now easily solve it by factoring. In particular, we can extract the greatest common factor of x, and that leaves behind x minus 4. So setting each factor equal to 0 and solving for x, we have two apparent solutions, x equals 0 and x equals 4. But again, you want to be very careful with these radical equations because sometimes they generate extraneous roots. So I am going to take the time to check both of them. So looking at our original equation, I'm going to replace the x first of all with 0 on both sides and check for balance. Under the radical, 2 times 0 is 0. We end up with the square root of 1 on the left, and on the right we have negative 1. Now, the square root of 1, the principal square root here is 1. Notice I'm not applying the square root to both sides. If I were, I would need the plus or minus. But if I'm just calculating a radical, we only recognize the principal or the positive square root. So look at our equation. We have 1 equals negative 1. That's certainly not true. Since we don't have a balanced equation, the 0 that we used is not the correct solution. That's an example of an extraneous root. Now, if I go back to this stage of the problem, it would certainly solve this quadratic equation, but essentially we increased the degree of the equation right here when we squared both sides, gaining an extra root. So it's not always going to be the case that your solutions you come up with solve the original equation. So we will not include 0 in our solution set. Let's check our other solution, which is 4. So I'm going to the original equation and replacing the x's on both sides with a 4. So under our radical, we have 8 plus 1, or 9. Square root of 9 on the left, 3 on the right. That one does give us a balanced equation, so we will keep x equals 4 as the only solution. Sometimes both of them work. Sometimes neither of them work. Sometimes one works. Radical equations are a little more unpredictable. Okay, let's finish with example C. So on this one, we just want to observe that we're dealing with a cube root as opposed to a square root. It's not a big deal. Our goal is still to isolate the radical and cancel it, but instead of squaring both sides, we're going to cube both sides. In the same way that a square root and a square cancel each other out, cubing something and taking the cube root are inverse operations, so they cancel and we end up with just the radicand. So we have 4x plus 5 on the left side, negative 1 to the third power, which means negative 1 times negative 1 times negative 1 gives us negative 1. And then our resulting equation is linear. So to solve the linear equation, we know isolate x. So I'm going to subtract 5 from both sides and then divide both sides by 4. And let's go ahead and reduce that by a factor of 2. So we end up with a parent solution of negative 3/2. And let's be sure and check by substitution. So I'm going to go to my original equation and replace the x with negative 3/2 and find out if that's equal to negative 1. Now 2 goes into 4 twice, so 2 times negative 3 gives me negative 6, and negative 6 plus 5 is negative 1. So under the radical we have a negative 1, and notice the cube root of negative 1 is negative 1. We got a negative 1 over there on the right side, so we have a balanced equation. So remember, if you have a single radical, your goal is to isolate it and then eliminate it by raising it to an appropriate power, squaring both sides, cubing both sides, etc. Once you do that, that will lead you to another type of equation. In our case, we found linear equations and quadratic equations as the result, and it was necessary to apply appropriate methods that we had learned previously to finish solving those equations. And while you should always check your solutions to every equation that you solve, you especially want to check them with radical equations to disregard those extraneous roots.